Okay. Good afternoon, everyone. Here we present the webinar on mathematical modeling of spread of COVID-19, organized by the Department of Mathematics, Ramakrishna Mission Residential College, Narendrapur, in collaboration with Department of Mathematics, Bidhan Chandra College, Rishra. Now, I request Dr. Ramesh Kaur, the principal of Bidhan Chandra College, uh, to deliver the welcome address. Sir.
Thank you. Good afternoon, everyone. Respected Principal Maharaj Narendrapur Ramakrishna Mission, respected distinguished research person, honorable dignitaries, dear colleague, research scholar, joint organizing committee secretary, coordinator, and affectionate student. It is really a great pleasure and privilege to be present in the webinar organized jointly by the Ramakrishna Mission Narendrapur, Department of Mathematics, and our college. Being the head of the institute, I must congratulate the teachers of the Department of Mathematics of Narendrapur Ramakrishna Mission and also our college, especially Dr. Naniopal Mandal and our faculty member Dr. Mohammad Saifuddin, as they have taken initiative to organize the webinar. First of all, I on behalf of Institute must welcome the respected research person Dr. Krishna Pada, Assistant Professor, Department of Mathematics, Mahadevananda, Mahavidyalaya. I would be immensely grateful as he has responded to our invitation despite his busy schedule. I convey my best wishes to our governing body, President and all members of governing body for moral support to organize the webinar. I must convey my sincere gratitude and deep cordial reverence to respected principal who has kindly sought out consent to organize the webinar collaboratively, to which we readily responded with a positive note. I do hope that our participant would reap a sound harvest from the day's discussion. I firmly believe that this kind of webinar would open up a positive rapport among the student teachers of both our colleges. The survey of the day's speech and reciprocal discussion, I do hope, would further illumine the minds of the teachers and taught. I wish a warm success of the day's webinar. Once again, thanking you all. Namaskar. Hello. 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 Can I audible? Hello.
Thank you, sir. For due to some technical issues, there is a delay. Thank you, sir. Thank you for your kind words. Now, here we are pleased to have Dr. Krishna Pada Das, who is the speaker of today's webinar. Dr. Krishna Pada Das is a faculty of Mahadevananda Mahavidyalaya for past 10 years, and he has done his graduation in mathematics honors from Calcutta University, and he has done his master's in applied mathematics from Calcutta University. He obtained his PhD degree from in Indian Statistical Institute, Kolkata. So now here Dr. Krishna Pada Das will present his uh, lecture. Sir.
Thank you whole organizing team for short introduction. Also thanks to principal of Rishra Bidhan Chandra College. Now I start our lectures. Uh, my topics is mathematical modeling of the spread of COVID-19. So first we give some outline of my lectures. So basic growth curve models, introduction of coronavirus disease, basic reproduction number, numerical simulation result and conclusions. Uh, we give some first introduce some basic definitions which are related to mathematical models and it's help to first learner of biomathematics. What is the population? A group of organisms of the same species living in the same habitat at the same time, where they can freely interbreed. So now how can population change? So there are four factors: natality, mortality, immigrations. Immigrations are the four factors which are responsible for change of populations. So now I can give the explain such type of four factors. What is the natality? It increase the population size. This species will have its own maximum birth rate. Maximum birth rate are seen when conditions are ideal. This can lead to the exponential growth. Now, the what is the mortality? Mortality reduce the population's growth. It operates more when conditions are not ideal, overcrowding leading to competition, spread of the infectious disease. The immigration is increase the population growth. It operates when population are not completely isolated. So what is the e-migration? It's decrease the population growth. It operates when population are not completely isolated. So the growth equation can be written as growth equation written as mortality plus immigration minus mortality plus e-migrations. So this is the growth curve. There are four stages of the growth curve: stage 1, 2, and 3. Stage 1 is the exponential growth curve, and stage 2 is the decline stage. That is the transition stage, and stage 3 is the stationary stage. So now I explain these four three stages. Phase 1, that is the exponential phase. Unlimited population growth, the increasing growth rate increases. Abundant food, no disease, no predator, etc. In phase 2, that is the transition phase, limiting factors slowing the population growth. And stage 3, this is the stationary phase, no growth, the limitation factor balance population capacity to increase. The population reaches the carrying capacity K of the environment. Added the limiting factors will lower the carrying capacity K. Removing a limiting factor will raise the carrying capacity K. The factor affecting carrying capacity, food supply, infectious disease, parasite, competition, predation, and nesting sites. Now I come into the growth curve models. The first we introduce the exponential growth curve. Suppose at time t, n is the number of the populations, and dndt is the rate of change of the populations. Dndt divided by n is the per capita rate of change of populations, and b is the birth rate, per capita birth rate, and d is the natural death rate, per capita death rate. So b minus d is the resultant birth rate, which is called all r, and it is called the intrinsic growth rate of the population. So dndt divided by n equal to r, that is dndt equal to Rn, which is the exponential growth curve of the population. Now we integrate, we get at any time t, the population in t equal to n naught. N naught is the initial value of the population e to the power rt. R is the intrinsic growth rate. If R is the positive, then we can get the exponential growth curve for values of R is 0.05. Now, give the anatomy of the equation exponential part exponential growth curve. So d and dt is the rate of change of number of the species, and R is the per capita rate of increases, N is the number of the individuals. So this is the anatomy, and if we integrate these equations, we get this equation, and n of t at any time t, the number of the population, n naught is the initial value of the population, and e to the power t. We get that this is the at any time of the populations. This is the anatomy of the exponential growth curve models. So we give some now example of the exponential growth. Test species show exponential growth if the human provide them with a perfect environment. Alien species, when a new species is introduced accidentally or deliberately into a new environment, it has no natural predators or disease to keep it under control. So now come into the logistic population growth. The environmental liberation is incorporated into the model of exponential population growth curve model. Then the exponential growth curve model converted to logistic population growth curve model, and which is characterized by the sigmoidal curve. This sigmoidal curve has the three stages. First is the population grow rapidly, and in the middle position population grows slow. After that, the population converges to the carrying capacity. And so this is the sigmoidal curve, and which is characterized by the equation of the logistic growth curve equations. So next we come into the logistic equations. If we include n by k in the exponential equations, 1 minus n by k in the exponential growth curve equation, then the exponential growth curve equation converted this equation, and this is called the logistic equations, and n by k is called the resistance of the environment, k is the carrying capacity. So now I give the anatomy of the logistic equation. So there is a DNDT, the rate of change of the populations, and R is the per capita rate of increase, and N is the population size at any time t, K is the carrying capacity, and the equation, the curve of this equations can be written as this, which is the sigmoidal curve, which is explained in the earlier slides. So we can give the next slide. So we give some example of predator prey species. This is the some predator prey species. Now we explain the what is the predator prey cycles. So it is a very important in a predator prey equations. First stage, there are two prey species. In absence of predator, prey species increases, and two prey species goes to four species. And in presence of prey species consumed by predator, and prey species decreases, and four prey species becomes one prey species. And in absence of prey species, predator species decreases, and when predator species decreases, then the prey species increases. That is the predator prey cycles. So this is the predator prey cycles, and now we give this slide will reflect the general predator prey equations. So X is the prey populations, and Y is the predator population. F of X is the growth functions of the prey species, and H of XY is the predation functions. Predation function, and GY is the mortality function of the predator populations. E is the conversion efficiency after predation of prey by the predators. So this is the general form of predator-prey equations. So we give a more early predator-prey equation, that is the Lotka-Volta models. Here R is the intrinsic growth rate of the prey population X, and A is the predation rate, M is the mortality rate, and B is the predations after predations. B is actually E into A. A is the conversion efficiency. So this is the Lotka-Volta system for predator prey systems. So now come into our main part of our lectures, that is called the coronavirus disease. So I introduce some introduction for in this regard. So coronavirus is the main major pathogen that primarily target the human respiratory system. In the last December of 2019, a cluster of patients were admitted to the hospital with initial diagnosis of the pneumonia of the unknown etiology. These patients were epidemiologically linked to seafood and wet elements wholesale market of one city of China. The early report predicted that onset of the potential coronavirus outbreak given in the estimated reproduction number 2019 novel coronavirus, that is COVID-19 named by the WHO, was which was the deemed to be significantly larger than the one. The range from 2.24 to 3.58 as of January 30 to 2020. 7,734 cases have been confirmed in the China, and 90 other cases have also been reported from number of the countries that include the Taiwan, Thailand, and Malaysia, Nepal, etc. Now we give the symptoms of the COVID-19 disease. So symptoms of the COVID-19 disease infection appear after incubation period approximately 5.2 days, and the period from the onset of the COVID-19 symptom to the death range 6 to 41 days with a median of 14 days. The period is depend on the age of the patients and status of the patient's immune system. It was the shorter among the patient greater 70 years old compared to those under age of 70. The most common symptom at the onset of COVID-19 illness are the fever, cough, fatigue, while the other symptoms include the stomach productions and headaches, diphtheria, and pneumonia, so etc. However, as there is no medicine and vaccine to coronavirus disease, we have to pay attention to techniques how we can prevent the disease propagations. And for this, we have considered the different coronavirus model with various parameters such as quarantine as well as isolation. We have observed the role of reproduction number for preventing the disease propagation in terms of the quarantine and isolation parameters. So reproduction number is a very important factors for epidemic models for controlling the disease. So we first introduce the what is the reproduction number. The reproduction number is the number of the newborn infectious species in a life period of a infected populations. So first we derive mathematically from a simple predator-prey models. We derive the basic reproduction number. So we consider here a simple predator-prey model. X is the prey population, P is the predator populations. So this is the logistic growth of the prey populations, and this is the predation functional form, and E is the conversion efficiency, D is the natural death rate of the predator population. So this is the predator prey models. Now we calculate the reproduction number for these models. So first we calculate the equilibrium point. So what is the equilibrium point? Equilibrium nothing but if you x dx dt equal to 0 and dp dt equal to 0, and we solve this system of equations, we get the equilibrium point. So the most important equilibrium point is the predator-free equilibrium point K0, and at this equilibrium point we calculate the Jacobian matrix this, and the eigenvalue of this Jacobian matrix is the minus r and this quantity. So this quantity is negative, then the equilibrium point EP will be stable, and under these conditions we get R0. R0 equal to 1 by EAK divided by BK, which is less than 1, and R0 is the called the ecological basic reproduction number. Now we explain the number. This is the birth rate of the predator at the equilibrium point level EP, and 1 by D is the mean lifespan of the predator. Subsequently, their product gives the mean number of newborn predators by a predator, so which can be interpreted as a ecological basic reproduction number. And it is noted that this term is first explained by Hilau. So now we calculate the basic reproduction number in a basic epidemic model. So first we consider SI epidemic model where there is no natural death or birth rate. Here we consider just without consider the SI epidemic model without demographic issue, that is the natural birth and natural is absent here. So beta is the transmission rate between susceptible. S is the susceptible population, I is the infected population. So beta is the rate of infection. So minus beta Si, that is the infection spread rate among the susceptible species. After infection, this part is come here, and Y is the disease-induced mortality of the infected predator. So from this equation, so we can calculate the basic reproduction number. At the initial stage, S is very greater than I. So we can take S equal to some S naught, and we calculate the basic reproduction number. So let I equal to I naught e to the power mt be the solution of these equations, and we put this equation and we get I equal to I naught e to the power this. If this part is negative, then I tends to 0. So this is the negative, I is tends to 0, and from this condition we get beta is not divided by gamma, which is called the reproduction number. This is basic reproduction numbers. So if R0 less than 1, I tends to 0. The system will be disease free. If R0 greater 1, then the infected population grows exponentially, and as result the system will be endemic. So R0 called the basic reproduction number. Here beta is naught is the newborn infected predator, and 1 by gamma is the lifespan of the infected individual. Therefore, the basic reproduction number can be described as the total number of newborn infected individual by infected individual in its lifespan. And now we derive also from another models, predator prey models, where disease circulating in the prey species. So prey species X is divided into two parts. One is the susceptible part and one is the infected part. So susceptible part prey species shows the logistic growth equation. Beta is the infection spread between susceptible to infected, and this is the predation term by the predator. So after predation, we get contribution from predator equations. Another predation by the predator to infected prey, and this is the contributions, and D2 is the natural death rate of that. This is the system of a predator prey system where disease circulating in the prey species. So now we calculate the basic reproduction number from this model equations. So first we calculate the equilibrium points. There U1 is the equilibrium points, and this is free equilibrium point E2, the predator free equilibrium E3. So first we calculate the Jacobian matrix around these equilibrium points U1, and we get this Jacobian matrix. And from this Jacobian matrix, we obviously the eigenvalues of this Jacobian matrix are minus R, and this quantity and this. If this quantity is negative and this quantity is negative, the equilibrium point U1 will be stable, asymptotically stable. So this is the negative, and this negative, which implies the disease reproduction number dk by d1. This is the basic reproduction number for the ecological part. So this is less than 1. Now we calculate the Jacobian matrix for around the equilibrium point E2, and from this Jacobian matrix we get the equilibrium the eigenvalue, that is the this is the eigenvalues, and if this less than 0, we get the disease basic reproduction number R0. Now another equilibrium point E3, we calculate the Jacobian matrix, and we get from this Jacobian matrix is this is the eigenvalues of this Jacobian matrix. If this less than 0, which implies the reproduction number R0, So this is the basic technique from the derivation of the calculation or derivation of the basic reproduction number from the eigenvalue techniques. So now we explain the derivation of R0 from the SIR models. So here we consider a susceptible infected and recovery model in case of coronavirus disease. If we consider the recovery, this is the susceptible infected are models. That is here we cannot consider here the demographic issue. That is there is no natural death or birth rate. So if we calculate the basic reproduction number, we have to that what is the condition for epidemic. The epidemic occur when the number of infected individual increases. That is DIDT equal to greater 0. Under this condition, at the onset of the COVID-19, early susceptible population is very large than the infected one. So we can say that S equal to S naught, and substituting S equal to S naught, we arrive that inequality, and from this inequality we get this quantity is called the R0, and it is the basic reproduction number. If R0 greater 1, then the number of the infected grow. If R0 less than 1, it will decay. Thus, R0 play the key role in the COVID-19 epidemic development. In particular, one can change the course of the disease dynamics by changing R0. For instance, it means the introduction of false value of R0 below 1, and the exponential growth changes to the exponential decay. So interesting, this is the exactly what happened in the China after restriction on daily life were introduced. The classical SIR model therefore determined the condition of the disease development from the comparison of the disease transmission rate and the sum of the recovery rate. In the other word, we compare the rates of the adding and removal of infected. The model does not account for the incubation period of the disease that was shown to important in case of the coronavirus spread. Individual can become infected before showing any symptoms. So now we you described another technique for derivation of R0 from next generation matrix. So here we define a matrix G equal to A, B, C, D. That is and dominant eigenvalue of this G matrix this. Now, how we calculate the next generation matrix? So there are two parts of the next generation matrix, F and V inverse, where F is the del Fi x naught, del Xj. X naught is the disease-free equilibrium point of the system. V del Vi x naught del Xj. Fi is the new infections, while Vi is the transfer infection from one compartment to another. X0 is the disease-free equilibrium point. So I0 is the dominant eigenvalue of the matrix next generation matrix G equal to FV inverse. So now we consider the ACIR model and calculate the basic reproduction number from this ACIR models by the help of the next generation matrix. So here S is the susceptible species, I E is the exposed species, I is the infected, and R is the recovery. So now we first calculate the F and V inverse. So first F we calculate at the disease-free equilibrium point, F is this, and V is also at equilibrium point, it's a disease-free equilibrium point this, and we calculate the R0 from FV inverse. So that is the R0 equal to this. Here, interesting note that R0 is the product of the rate productions of the new exposed and new infection, as it should be. It can be shown easily from the Jacobian matrix around the disease-free equilibrium point. If R0 less than 1, the disease-free equilibrium point will stable. This implies that disease can be wiped out from the system. If R0 greater 1, the disease-free equilibrium point will be unstable and disease will be endemic in the system. So R0 is the increasing function of two important parameter beta and A. If effective contact rate of beta is increases, the unknown disease such as COVID-19 will be spread in the community. If the birth rate A of the susceptible individual increases, the value of R0 will be increased, and which implies that COVID-19 transmit among the community rapidly. So we conclude that R0 is the controlling parameter for spreading the COVID-19 disease transmissions. Now we come into the basic model, ACIR model. ACIR model. So we consider that is the ACIR complete ACIR models. The here S is the susceptible, E is the exposed individuals, I is the infected individual, R is the recovered individual, A is the recruitment of the susceptible individuals, and this is the transmission between S and E. This is the transmission between S and I. So this is the complete compartmental models here. Now we examine the stability and equilibrium point. After some transformations, the model can be changed these equations, and we calculate, we use the variable nt equal to st plus et it and rt. Using this variable change, the system of equation can be reduces these equations, and after calculation of the Jacobian matrix, we calculate the two equilibrium point L0 and L star. So after Jacobian matrix around the L0, we get the eigenvalues from this, and we get the basic reproduction number this, and which is less than 1 when the L naught is stable. Another Jacobian matrix around the equilibrium point L stars. So that is the L star around this, and we calculate after calculation of the characteristic equations, we get the condition of the local stability, that is the route criteria, and we get lambda 1 beta 0. So this is the condition of the stability of the L star. Now we model validation and parameter estimation. So in this section we estimate the parameter value from real data of COVID-19 disease to occur in the Italy. To validate our model and estimate the important model parameter, we have fitted the model with real COVID-19 case from Italy from 15 February to 4th April using the nonlinear least square principles of the package. The least square principle is given below. Here, CI is the cumulative number of infected population in real cases, and CIP is the cumulative number of the model predicted infected population on ith day. Then our target is to minimize these functions for all parameter theta belong this. Using this principle, we estimate our parameter values. For this parameter value, we draw the curve model curve, that is the blue dotted is the model curve prediction. So that is the this shows that the infection is growing exponentially, and also data value from data is the data result is shown by the red dot, and red dot also shows the the infection increases exponentially, and which is similar to the model result. And corresponding also bar plot also has been shown that if his days increases, the infection is grow exponentially, and we have corresponding residual plot rate here. So this is the our result is model result is very close to the our data result. So that is here also is the already we explained that. So we skip this. Now we predict the result from on the basis of the our 50 days data. We predict our model result uh, 140 days. So that is the we have blue is the model predicted result 1.140 days 140 days on the basis of the data 150 days. So that is the we can take the 110 days. After 110 days, we observe that the card is flat. So it can be shown that after 120 days, the disease can be stabilized, and the exponential growth can be stopped. This can be shown by our bar plot here also. So already we described this in figures. So in this conclusion, in this paper, we considered the four-dimensional epidemic models to investigate dynamics of COVID-19 and use it to predict the situation of the corona in the Italy. We have first derived the equilibrium points and their existence. We have also worked out the local as well as global stability of different equilibrium point under some threshold condition. We have pay attention to the basic reproduction, which is very important for preventing the spread of the disease propagation. We have derived the basic reproduction number from our proposed model. We have observed the stability of disease free as well as endemic equilibrium point locally and below in terms of basic reproduction number. To validate our proposed model, we have used the data set of the country of Italy and we have estimated the parameter values and observed the disease dynamics from our model result and data result. First, we have observed the result of 50 days for Italy, and we have found that the infection have increased among the community exponentially from data and model simulation result. It has been justified by bar diagram plots as well as residual fit. Finally, we have predicted the result of 140 days for spreading the disease among the community. It is noticed from our model simulation result that infection will be increased up to 120 days, and after that, the spread of the disease is among the community will be decreases after 120 days. It will be stable. However, our model prediction result will be helpful to policymakers and management strategies. Now we introduce the another models where we include the asymptomatic and symptomatic part. So the here we model here is S is the susceptible, E is the exposed, A is the asymptomatic individual, I is the symptomatic individual, R is the recovery. This is the coronavirus model. So I include the symptomatic and asymptomatic part. In this model, we calculate the basic reproduction number by the help of next generation matrix. So we first calculate the disease-free equilibrium point. So that is the disease-free equilibrium point, and we calculate the matrix F and V inverse at the disease-free equilibrium point. That is F is this and V is this. So we calculate the basic reproduction number R0 V inverse F V inverse and basic reproduction number R0. And after some numerical simulation, we critical levels. Here one is the critical level. If R0 greater 1, the disease can be endemic, and if R0 less than 1, then the disease goes to the extinction. So this is the curve of R0 in against the beta is the course of infections. So we use already described in this graph. So it is skips that. Now we plot in the different level of infections. We plot the R0 value of the R0 in case of recovery parameter. So if we increases that recovery parameters, then R0 value is decreases. So recovery parameter is very important for controlling the disease dynamics. So we have another recovery parameter here, and we the different curve is shows that different level of infections. So R0 value is decreases when and recovery is increases. So this different recovery parameter is the very important for controlling the parameter. Now we introduce another COVID-19 model that is that include the quarantine part. S is the susceptible part, E is the exposed, Q is the quarantine, I is the symptomatic part, R is the recovery. So here we use that S is the susceptible, exposed, quarantine, asymptomatic, I is the symptomatic and recovery. This is the whole part where considered three most important compartment. One is the quarantine compartment, another is the asymptomatic compartment, and another is the symptomatic compartment. And from this model, we calculate the first we observe the Fi and Vi and calculate the F at the disease free equilibrium points F and V, and we get the matrix FV inverse, and we calculate the basic reproduction numbers. If we derive R0 with respect to quantine parameters, and this quantity is less than 0 or greater than 0, and we get a critical value of quantine parameter. So below that quantine parameter, dr R0 is decreases, and if the critical value, quantine value increases this critical value, then the R0 is increases. So this is the card for the R0 against the force of infection, and it is the critical level 1. And if we force of infection increases, then the value of R0 increases, and disease will be endemic. So here we also give some values of R0 with respect to recovery parameters here, gamma 1, and we get that if we recovery quantine, actually this is the quantine parameter. So this, if the quantine parameter increases and the value of the R0 is decreases. So another recovery parameter also here. We observe that the value of the R0, value of the R0 is decreases with respect if the recovery parameter increases. So recovery parameter and quantine parameter very important for controlling the disease. This another observation of R0 with respect to the recovery parameter. If the recovery parameter increases as an R0 is decreases, we observe different level of infection. ABC is the different level of infections. So from this we described already in the figure. So it is a skip, and it is noticed that if the relative infectionness of the quantine individual QR will not cross the critical value R gamma 1, the value of the reproduction number decreases, and as a result of the spread can be decreases, but the relative infectiousness quantine value will cross the critical value, then the value of the reproduction increases, and it is disease burden will be increased among the community. It is observed the recovery parameter may help important role for preventing the spread of the disease. So this is our reference, and thank you.
Thank you, sir. Thank you for such a nice presentation. Now, if anyone has any questions from the audience, they can ask in the YouTube live chat. So, is there any question? Okay, if there is no question, then please let me know. Okay, there is no question, so we carry on. So now I would request uh, the faculty of Department of Mathematics, Bidhan Chandra College, Dr. Mohammad Shoifuddin, to give his vote of thanks. Sir, over to you. Sir. Okay.
Thank you very much, Sumit. Good afternoon, everybody. It's my privilege to have been asked to propose a vote of thanks on this webinar. On this auspicious day, on behalf of Department of Mathematics, Narendrapur Ramakrishna Mission Residential College, and Bidhan Chandra College, Rishra, I would like to express my gratitude to the principal of Ramakrishna Mission Residential College, Narendrapur, Swami Shastra Gyananandaji Maharaj, and principal of Bidhan Chandra College, Rishra, Dr. Ramesh Kaur sir. And also, I want to express my gratitude to the head of the Department of Mathematics of Narendrapur Ramakrishna Mission Residential College, Dr. Norigopal Mondal sir, and IQAC coordinator of Bidhan Chandra College, Rishra, Professor Sadhunath Kundu sir, for providing encouragement and inspiration to organize this webinar. I also wish to express our sincere thanks to Dr. Krishna Pada for giving a nice presentation on the topic mathematical modeling of spread of COVID-19. I also extend my thanks to my motivated and dedicated colleagues of Department of Mathematics of Bidhan Chandra College, Rishra, and Ramakrishna Mission Residential College, Narendrapur, for their enormous inspiration regarding this webinar. Being an ex-student of Narendrapur Ramakrishna Mission Residential College, I feel proud for organizing this webinar in collaboration with my present college, Bidhan Chandra College, Rishra, and previous college, Narendrapur Ramakrishna Mission Residential College. I also extend my thanks to all the audience and active participants for their active cooperation for the successful completion of the webinar. I would also like to thank Professor Vishwadip Pal, Department of Mathematics, Narendrapur Ramakrishna Mission Residential College for technical support of this webinar. Thanks to all of you.
Thank you, sir. Now, thank you, Dr. Krishna Pada to join us, and we are pleased to have you with us. So here we end this webinar. Have a nice day, everyone.